day, our dear senior high school learners, and welcome to DepEd TV. I am Sir Tony, and I would like to welcome you all to our COP9 Headquarters. By the way, COP9 is the Filipino term for chemistry. Together with my team, this headquarters is where we conduct experiments and researches amidst the pandemic we have right now. Because we believe that nothing should stop us from discovering new facts and helping people. We're always at your service. Together, let's unleash the saysay at husay ng inyong mga sarili as we explore the exciting world of physical science. Everyone is welcome to join us in this learning episode. Just make sure that you have your pen and paper ready so you can write down what you will learn today. In our previous episode, we learned about how artificial elements are made or utilized in laboratories. You also learned about the development of the periodic table of elements and the notable scientists behind this important scientific achievement. Today, we are up for other amazing discoveries. Join me as my apprentice and let's learn about the polarity of molecules. As my apprentices, your task is to equip yourself with scientific knowledge that you can eventually use to help people in need. Don't worry, I am here to guide you in your mission. In our headquarters, expect that we will be receiving calls from people who are encountering scientific problems. And as the saying goes, for every problem, there is a solution. I'm sure that you will be part of the solution. Just be focused, disciplined, and determined till the end. All right, for your first learning task, I want you to meet Professor Aldin Richards, a molecular chemist who is known to have synthesized molecules with new properties to address scientific and societal challenges.
Oh, hello there, bright minds. I am Prof. Aldin Richards. Because sharing is caring, I would love to share my knowledge about molecules. A molecule is a group of two or more atoms held together by chemical bonds. It's like the kind of bond that you have with your family, your friends, or with your special someone. The bond that keeps you tight and close. I can see and feel that you got a bit kilig when I mentioned special someone. Let us now move on before this conversation leads us to something else. Some common examples of molecules are water, which is made up of two hydrogen atoms and one oxygen atom, and sodium chloride, or table salt, which is made up of a sodium atom bonded to a chlorine atom. Actually, there are millions of different molecules that are present in nature, and here are some of those. Ozone. It acts as a shield to protect the Earth's surface from the sun's harmful ultraviolet radiation. Next, listen up, plantitos and plantitas. We have nitrogen. It is actually considered the most important component for supporting plant growth. We also have ethyl alcohol and isopropyl alcohol that we use as disinfectants, preventing the spread of the deadly coronavirus. Molecules also comprise the structure of our favorite food, such as sucrose or table sugar, caffeine in coffee, theobromine in chocolates, capsaicin in chilies, and menthol that gives us that minty, cooling odor and taste. Let us not also forget the important molecules that make up medicines and supplements like aspirin and paracetamol, which are used for relieving minor aches and fever. And finally, to strengthen our immunity, let us bear in mind to have our daily dose of vitamin C or ascorbic acid, a powerful antioxidant that can strengthen our body's natural defenses. These are just some of the many important molecules that comprise our environment and the substances we use every day. Interestingly, we humans have also developed many ways to classify or sort them. My dear apprentices, remember, the properties of molecules highly depend on their structure and the arrangement of their atoms in space. Because of this, their classification also varies due to their structural and geometrical differences. Oh, wait a second. We have a call. COP9 Headquarters, great day. This is Professor Richard. How may I help you?
Hello, sir. This is Mr. Hydro. I would like to ask for some help. I need to decode certain unidentified words in my computer system so I can finally activate the bonding sequence of the unknown substances I'm investigating. Can someone from your team help me deal with this?
Don't worry, Mr. Hydro. We are here to help you out. Will you please show to us the words that we need to decipher?
Okay, for a while, here they are.
Let's try to figure out these words as fast as we can. Ready? Let's begin. First word. Brilliant. Lone pair it is. Lone pair pertains to the unshared or non-bonding pair of electrons found in the outermost electron shell of the atom. We're doing great. Let's try the next. Did you say polar bond? Then you are correct. A polar bond is a bond that forms partially positive and partially negative ends or poles. Let's proceed to the third word. I know what you have in mind, the opposite of the previous word. Yes, the word is non-polar. Wow, the next word seems to be a long word. I think it begins with an E and ends with a Y. What do you think is the answer? All right, electronegativity. It is an atom's tendency to attract electrons to itself in a chemical bond. Here's the last and we're good to go. Two words. The beginning letters are M and G. Excellent! Molecular geometry, the three-dimensional arrangement of the atoms and chemical bonds in the molecule. Congratulations, my dear apprentices, for a job well done.
Thank you so much for helping me. You're the best. I'll update you on the development of my investigation. Goodbye for now. Thank you, Prof.
You're very welcome. Thanks, my brilliant apprentices. That's it for now. Let me bring you back to Sir Tony. Good luck and keep up the good work.
Wow, you did well in your first task. Are you excited for more? Earlier, you have learned that the properties of molecules highly depend on their structure and the arrangement of their atoms. At this point, I would like to share one of the ways on how we can classify molecules, and that is through their polarity. Polarity refers to the distribution of the electric charge around atoms, chemical groups, or molecules. Polar molecules are also called dipoles, which means two poles, having a positive and a negative charge. One example of a polar molecule is water. We all know that life exists on Earth because it has enough water. In this time of the COVID-19 pandemic, water is very essential because washing our hands frequently is one of the best ways to prevent the spread of the coronavirus. You might also have heard before that water is the universal solvent. It is very capable of dissolving a lot of substances. Alright, now is the time for you to meet another resident chemist in the COP9 headquarters, Professor Paulo Besper. He specializes in stereochemistry, the branch of chemistry concerned with the three-dimensional arrangement of atoms and molecules and the effect of this on chemical reactions. Good day to all of you! I've heard that you're all doing great as Sir Tony's apprentices. Well, let's see how far you can go. Are you still up for the challenge? I will be sharing my expertise on determining the polarity of molecules. Well, it all boils down to two factors. First is the polarity of bonds, based on the electronegativity difference of the atoms involved. And second, the geometrical shape of the molecules, which can be predicted via the valence shell electron pair repulsion theory, or BSEPR theory. Before we continue, let me ask you, how do you become attracted to a certain person? Maybe it's because of the person's personality, physical appearance, talent, or skills. You know what? Atoms do the same thing. An atom may pull or attract electrons strongly to it, while other atoms have less pulling or attracting power. Professor Richards mentioned earlier that electronegativity, or EN, is the measure of the ability of an atom to attract bonding pairs of electrons. This concept was first introduced in 1932 by Linus Pauling, an American chemist. Let's take a quick look at the electronegativity values of the elements on our periodic table. Do you notice something? Take note, our dear apprentices, that the electronegativity value increases within a period from left to right and decreases within a group from top to bottom. The higher the electronegativity value of an element, the more it tends to attract electrons towards itself.
Well said, Professor Besper. But what is the connection of electronegativity to the polarity of bonds?
Good question! We could use the EN values of the atoms involved to get the absolute electronegativity difference to help us predict what type of chemical bond would exist between them. If the EN difference is greater than 1.7, it is an ionic bond. An ionic bond is formed when there is a transfer of electrons from a metal to a non-metal, forming oppositely charged particles. Table salt or sodium chloride is a good example of this. The EN value of sodium, a metal, is 0.9, and chlorine, a non-metal, is 3.0. Getting the absolute value of their difference, or the positive value, we have 2.1, which is greater than 1.7. That's why it forms an ionic bond.
Sodium has 1 valence electron in its outermost shell, while chlorine has 7. Following the octet rule, sodium transfers 1 electron to chlorine. They both have 8 electrons in their outermost shell now. And since they have different charges, they attract and are bonded eventually.
Sodium and chlorine are indeed a perfect match. Moving on, if the EN difference is between 0.5 to 1.7, it is a polar covalent bond. On the other hand, if the EN difference is less than or equal to 0.4, then it is a non-polar covalent bond. Please take note that in polar covalent bonds, the atoms have an equal sharing of electrons. The bonded pair of atoms form an electric dipole represented by this symbol. A dipole is symbolized by an arrowhead pointing to the more electronegative atom. The negative pole, represented by lowercase delta minus, and a cross tail located in the less electronegative atom, the positive pole, represented by lowercase delta plus. Take hydrochloric acid or HCl for example. Chlorine has a higher EN value than hydrogen. Thus, the direction of the arrow is from hydrogen pointing to chlorine. There is also an unequal electron density as represented by the size of the circle or cloud that surrounds it. This is definitely an example of a polar covalent bond. This time, let's take a look at these two chlorine atoms. What do you notice with the distribution of electrons? Good observation! It forms a bond wherein electrons are equally shared, indicating a balanced distribution of the electrical charge. This is an example of a non-polar covalent bond. I hope I made myself clear with the facts I have mentioned. To make things easier for you, here is a table that summarizes the type of chemical bond that will be formed based on the EN difference of the bonded atoms. You just learned how to predict the type of bond polarity by calculating the electronegativity difference of atoms, specifically those containing two atoms. But how about those molecules consisting of more than two atoms? For polyatomic molecules, both the bond polarity and molecular shape determine the overall molecular polarity. In terms of molecular geometry, the valence shell electron pair repulsion or Besper theory, where my parents derived my name, would help us determine the spatial arrangement of atoms in a polyatomic molecule. At this point, I will let you witness one of the galleries here in COP9 Headquarters, the Molecular Geometry Gallery. Molecular geometry or molecular structure is the three-dimensional arrangement of atoms within a molecule. It is related to different properties like color, phase, magnetism, chemical reactivity, and the one that we are talking about, polarity. Behold, I now present to you the basic molecular geometries. The symmetrical molecular structure includes linear, tetrahedral, trigonal planar, trigonal bipyramidal, and octahedral. The non-symmetrical molecular structures are bent, trigonal pyramidal, and the diatomic elements. You can predict the shape or molecular geometry of a substance using the following steps. Step 1. Determine the central atom of the molecule. The central atom is the least electronegative element. Step 2. Draw the appropriate Lewis dot structure for the molecule. It is the graphic representation of the electron distribution around the atom. Step 3. Count the number of bonding and non-bonding pairs or the lone pairs around the central atom. Step 4. Determine the electron pair orientation using the total number of electron pairs. And step 5. Identify the shape or molecular geometry. Let us now predict the molecular geometry of carbon dioxide. Step 1. Between carbon and oxygen, carbon is the least electronegative. That is why it is the central atom. Step 2. The Lewis dot structure for carbon dioxide looks like this. Step 3. For the purpose of determining the position of the bonding pairs, we will count the double bonds formed as one bonding pair. Therefore, carbon dioxide has 2 bonding pairs of electrons. Step 4. The electron pair orientation for 2 electron pairs is linear. Step 5. The molecular shape of carbon dioxide is linear. Why don't you try to predict the geometric structure of the next molecule? Here it is. Chloroform. Step 1. What do you think is the central atom given the elements E and values? The least electronegative element is hydrogen, but in this case, it will not be the central atom. Why? This is because hydrogen has only 1 electron and can never make more than 1 bond. Thus, it can never be a central atom. Since carbon is less electronegative than chlorine, it will be the central atom. Step 2. Try to draw the Lewis structure. Does it look like this? Great! Step 3. As seen in the structure, there are 4 bonding electron pairs. Step 4. What do you think is the electron pair orientation for 4 electron pairs? Tetrahedral. Step 5. So, the molecular shape of chloroform is tetrahedral. Now that you have learned how to determine the molecular geometry, let us now identify the overall polarity of the 2 molecules that we have mentioned. I want you to study the flow chart here and use this as your guide to determine your answer. Carbon dioxide is symmetrically arranged as linear. The attached atoms to the central atom are also the same. Therefore, carbon dioxide is a non-polar molecule. On the other hand, chloroform, although it has a symmetrical arrangement which is tetrahedral, the atoms attached to the central atom are not all the same. There are 3 chlorine atoms and 1 hydrogen atom. That's why chloroform is a polar molecule. Congratulations! You have learned so much. It is an honor to have guided you today. I think Sir Tony is looking for all of you now. Till next time, bye! Welcome back, my dear apprentices. Time to test what you've learned from Professor Besper. Time to make him proud. Eyes on the screen, everybody. Your task is to identify which molecules are polar and non-polar given the Lewis dot structure and geometries of the molecules. We have ammonia, carbon tetrachloride, hydrogen bromide, and water. I'll give you 10 seconds to think and tell me your answers. So what are the polar molecules in our given examples? If your answers are ammonia and water, then you are correct. Of course, the 2 remaining substances, carbon tetrachloride and hydrogen bromide, are both non-polar molecules. If you got the correct answers, then you deserve a badge. Hello, this is Sir Tony of the COP9 Headquarters. How may I help you? Alright. Okay, I'll be there in 5 minutes. Someone needs our help about mixing substances. Let's go! Hello there, Victor. You've called the COP9 headquarters earlier because you have a problem. And I'm here to help you out.
Yeah, I've been trying to mix some amount of oil and water, but they seem to separate from each other. Did they have a big fight thousands of years ago that they hate each other forever?
You know what, Victor? They never had a big fight. The science of chemistry has an explanation for that. Water molecules are polar molecules. One end has a positive charge and the other end has a negative charge. This allows molecules to bond together. Oil molecules, on the other hand, are non-polar. Are you familiar with solubility and miscibility?
I think I heard that before, but I don't know. Could you tell me more about that?
Okay. Solubility is the ability of a solid substance to be dissolved in a given amount of solvent, like water. Miscibility is the ability of two liquids to combine or mix in all proportions. The general rule to remember is like dissolves like, or like mixes with like. This means that polar substances can only be dissolved or mixed with polar substances, while non-polar substances will of course be soluble or miscible with another non-polar substance. I'm sure you have already tried mixing coffee powder, salt, or sugar in water.
I did, sir.
Sugar and other polar molecules are described as hydrophilic or water-loving substances, and they love to be dissolved in water. They're able to bond with water molecules. Since oil is made up of non-polar molecules, oil will definitely not mix with water. Instead, they form distinct layers and usually float above water molecules. Oil and other non-polar molecules are described as hydrophobic, which means water-fearing, and they hate being dissolved in water. These molecules, however, dissolve with one another or other non-polar solvents, such as acetone, ether, or gasoline. But remember not to mix substances for no reason at all, okay?
Sure, Sir Tony. I've learned a lot. And next time, I'll take extra precaution in mixing substances. Thank you so much, Sir Tony.
You're very much welcome, Victor. I'm happy to be of service. That's all for today, and I hope you had a great time learning with all of us here in the COP9 headquarters. Together, let's all be heroes in our own little ways. I also hope that you will keep the bond between us strong and still find time to join us next week as we discuss intermolecular forces. This has been Sir Tony, and it has been an honor teaching you today. Continue unleashing the saysay and husay ng inyong mga sarili in everything that you do. Till next time, my dear apprentices, bye!